Okay, today's molecule of the day is called thalidomide. Anybody ever heard of this one? Yeah. So you know where this is going.
Yes.
So here's the structures of thalidomide. You'll notice they are almost identical. There's just one very small difference, and that is this one has got a hash bond here, and this one has a wedge. So these are stereoisomers. As we're going to find later today, they are enantiomers of each other, but they differ only by the spatial arrangement of the atoms around that carbon right here. So it's the late 50s in West Germany, and you are a scientist, and you've discovered that thalidomide does an excellent job of treating morning sickness in pregnant women. So for the next couple of years, this mixture of two isomers is prescribed to relieve nausea in morning sickness. And you can't isolate just one of the two because they go back and forth between each other in the human body. That's not super normal for two compounds like this, but it has to do with some acid-base chemistry, essentially. They can interconvert. Our thalidomide is active it's an antiemetic. It relieves nausea and vomiting. S-thalidomide is a teratogen. And a teratogen is something that causes, ironically, birth defects. And so the women that took this for their morning sickness had babies that looked like this. So generally speaking, missing arms and legs, or I think in most of these cases, just missing bones in the limbs. So they just had floppy limbs. And most of these kids grew up to have their arms or legs amputated, just because their mom took a medicine for morning sickness. So unsurprisingly, this was pulled fairly quickly when they realized, oh, hang on, one of the molecules or one of the forms of thalidomide does exactly what we want it to do. And in fact, it does it better for morning sickness than it does for nausea caused by other things, which is kind of the horrible irony of it all. But the other form, which is just like the left-hand, right-hand version, causes those awful birth defects. So that's the story of thalidomide. Okay. So the culprit here is the chirality of the thalidomide molecule. So an object, and notice I say an object and not a chemical because chirality, this applies to any object. Of course, we'll talk about it in terms of molecules. An object is chiral if it has a non-superimposable, so not superimposable, mirror image. And so the best example that you have with you, maybe these kids don't, unfortunately, that's your left and right hand. So your left and right hands are mirror images of each other, right? If there's, a mirror in between, they look identical through a mirror. But you can't superimpose your hands on top of each other and have them be identical, right? So if we keep the back of our hand pointing toward us, you put your hands on top of each other and they're not opposable because your thumbs don't match up. You can't go like this, that didn't work. if you try to go like this, it looks like they match up, but no, here, the back of my hand's facing you, and here, the palm of my hand is facing you. So those are two different things. So your hands are chiral. They have non-superimposable mirror images. So another example of a chiral molecule, or an example of a chiral molecule, is 2-butanol. We haven't talked about naming of alcohols, but that's okay. Here is one isomer of 2-butanol. So a 4-carbon chain with an alcohol on the second carbon. Alcohol is coming toward us because it's on a wedge. One important note here that I should mention is that having a wedge or a hash in your structure does not necessarily indicate that we have a chiral molecule. It's also not required to have a wedge or a dash in order to be chiral. So a lot of times we're going to see a molecule with a wedge or a dash in it, and we're going to go, oh, we need to look at stereochemistry. We need to see if it's chiral. Those don't necessarily mean the same thing. But in this case, this molecule is chiral. So like we did when we did Newman projections, I'm going to abbreviate all of the substituents around that central carbon atom and draw them all out explicitly. So a methyl group on that side, an ethyl group on that side, then the alcohol coming toward us. Doesn't matter if I write it a little bit to the left or a little bit to the right. And then implied, going backwards, is a hydrogen to give our carbon 4 bonds. So ethyl group, 2-carbon group on the right, methyl group, 1-carbon group on the left, the oxygen, and then the hidden hydrogen. Okay, so molecule is chiral if it's got non-superimposable mirror images. So we need a mirror image. We'll draw, there's our mirror. And when you're doing this in practice, when you're actually just going to draw the mirror image, just turn your brain off, okay? It's really easy to overthink drawing a mirror image of something because you don't even have to know any chemistry to do this. You just mirror the thing. Like you're looking through a mirror. So on the inside closest to the mirror, ethyl group, and we go outwards, then pointing in and going up, hydrogen, pointing out and going up, is the alcohol, and then the methyl group on the far side. These two structures cannot be superimposed even if we rotate them. So if you say, all right, let's take the first structure and just flip it over like pancake to get the second structure, let's see if that works. All right, so the methyl and ethyl group are going to get flipped around. That's fine. Okay, that we do have that. But what about the alcohol? All right. So if the alcohol is coming toward you, let's say methyl group's down here. So alcohol is coming toward you, methyl group's down here. We flip the pancake around. Okay, the methyl group, right, it's pointing down and to the right, but now the alcohol is pointing backwards. Okay, I didn't change the position of my hands, I just turned my body around. And so, no, they are not superimposable because in this one, the alcohol is coming toward us instead of away. All right, a chiral center is just the carbon atom that we're interested in here. And more specifically, it is a carbon atom. Technically, it can be another atom, but like another element. But for our purposes, we're just going to talk about carbon stereocenters, chiral center, stereocenter, anything, is a carbon atom with 4 different groups attached to it. And a lot of times we'll indicate a chiral center with an asterisk or a star or something like that. Not required. So what does it mean to have 4 different groups? That's kind of just like our example we already did. Okay, we've got a chlorine, we have a methyl group, we have an ethyl group, and we have a hydrogen that's not drawn. So that's 4 different substituents: chlorine, methyl, ethyl, and hydrogen. And so that carbon there is a chiral center or a stereocenter. Okay, we see a hash, and so we're like, this could potentially be a stereocenter or a chiral center. So on this carbon, we've got the OH group. We have an ethyl group on the left. We have this other group on the right, which is an isobutyl group, but doesn't really matter what it is. It's different from everything else. And then coming toward us, we have a hidden hydrogen. Okay, so that's 4 different groups. So that carbon is a stereocenter. What about that carbon? Is that a chiral center? No. Sorry, I keep finding myself saying stereocenter. Same thing. So no, the yellow carbon is not a chiral center because it's got this long group of the alcohol, all that stuff going left. It's got a hydrogen that we can't see. And then it's got 2 methyl groups. So those 2 methyl groups are identical. And so that precludes it from being a chiral center. So 2 of the same thing makes it not chiral. And the same goes for that carbon there. It's a little easier in this case. It's only got 2 bonds shown to it, so we know it has 2 hydrogens. And those 2 hydrogens are the same thing, so automatically not a stereocenter. Okay, these examples both have a wedge or a hash indicated, but that's not required. There's this molecule. And this has a couple different things going. First, we don't have a wedge or a hash. I think we can see what carbon might be the most interesting. But we don't have a wedge or a hash, and we have a ring. So what does the ring have to do with anything? So, well, we'll look at our suspicious carbon here with the bromine on it. And what does this carbon have on it? Well, it's got the bromine. It's got a hydrogen that's implied. And then it's got 2 connections to the ring. So if we go to the right or clockwise, we end up with this carbon and then a double bond to the next carbon. If we go clockwise, the left, then we get a carbon single bonded to a carbon, single bonded to a carbon, single bonded to a carbon, which is then part of the double bond. So if imagine you're driving along the road of the ring, right? Those rows are going to look different depending on which direction you go. So those are considered 2 different groups. Okay, so that makes that carbon a chiral center. What about the alkene carbons on the right? Okay, those are not chiral because, well, they've got a double bond. And if you've got a carbon with even one double bond, it can have a maximum of 3 things attached to it. So it can't have 4 different groups. So it's not a chiral center. So things to look for are a lot of things connected to one atom, right? All of these atoms that we found that are chiral are kind of busy looking. And that is very typical. Counterexample would be this one. But I think pretty clearly you can see the 2 groups are the same. Sometimes it's drawn a little bit less symmetrical looking than that, and that can kind of start to trip one up. Things you don't necessarily have to look for and can lead you astray are the wedge and root hashes, because here, those are both stereocenters, but this one does not have a wedge or a hash. In fact, it does, but we're saying we don't know which one it is. Okay, another example maybe is this. So is our central bromine carbon a chiral center here? Yes or no? No. So we have the same thing going that way and the same thing going that way around the ring. And so even though we still have a bromine and a hydrogen, the ring is the same substituent because it looks the same going in both directions. So that is not a chiral center. That would even apply if we had a wedge. Turns out that wedge actually doesn't mean anything because it's not a chiral center, but that's something I might do to be mean is draw that and ask you if that's a stereocenter or not. Okay, so make sure you look for those 4 different groups. Okay, we saw the example of 2-butanol where we made a mirror image and it was not superimposable. And we saw thalidomide, which these 2 are actually mirror images of each other. It's not quite as easy to see in this way, but they've also got a stereocenter flipped. That relationship is called, those 2 are called enantiomers. So molecules enantiomer is its non-superimposable mirror image. I already kind of showed you the example where we put the mirror on, like, have it go like sideways across the mirror like this. So take any molecule that has a chiral center. If you flip it, sorry, don't flip it, mirror it, you'll get a non-superimposable mirror image. And right, you can check to make sure that these are non-superimposable by saying, okay, this hand is the methyl group. Here's the chlorine coming towards you. If we mirror it, sorry, if we flip it around, compare it to the mirrored version, methyl group is going down and to the right. That's correct. But the chlorine, my chlorine's going back, but the chlorine in the mirror image is going toward you. So non-superimposable. And that means that these 2 molecules are enantiomers of each other. We use the word enantiomers like the word twins. Of course, they're not twins because that implies that twins are identical. Although they are similar, they certainly aren't identical in this case. Further, that analogy works because you can't have three siblings that are all twins. That's triplets, it's a different thing. And so you can only ever have a pair of enantiomers. You can't have three molecules that are all enantiomers of each other. We'll see examples of that in a moment. What's more useful, I think, than doing the mirror side to side, and this is a bit more difficult to draw, but it's easier to actually do, is to have the mirror be behind, like a mirror usually is when we're looking at it. Okay, so the molecule here is in front of our mirror, and so here you're going to think like you're looking in a mirror, right? So the chlorine, okay, we're leaning back. Chlorine's leaning back, right? So if you do this in front of the mirror, which way is your reflection leaning? Away from you, right? So into the board. I'm not that excited about enantiomers. Okay, so your reflection is leaning now back away from you in your reflection. Okay. This is easy, right? The skeleton, the shape of the molecule has stayed the same. All we've done is switch the wedge and the dash, right? So wedge becomes hash. Becomes wedge. So that is the easy way to generate a molecule's enantiomer. Just take all of the wedges and dashes and flip them. There's another relationship. It's called diastereomers. It's not as close of a relationship. Okay, the diastereomers are less similar to each other than enantiomers, but we'll talk about that after we sort of quantify different enantiomers. Not really quantifying, but we can specifically designate a chiral center as being left-handed or right-handed. Now, I don't know about you, but if I look at these two chlorobutane molecules, it's not immediately clear to me that one looks right-handed and one looks left-handed. That didn't really come natural to anybody. But there is a process, a followable list of steps that we can follow to get this correct. So every chiral center can be labeled left to right-handed, but we don't call them that. We call them left-handed is S. Actually, I got the colors backwards from the thalidomide example, so I won't use colors. Left is S, and right is R. So right starts with R. That's probably the best way to remember that. If you want help with left being S, S is basically the Latin sinister. And left is bad. It's the wrong hand to write with. Any other lefties in here? We know that's not true, but I can remember that because I'm left-handed and My grandpa was made to write with his right hand. Anyway, but R is right-handed. Okay, so the list of steps that we need. The first is to prioritize the 4 groups on the stereocenter. Turns out it's going to be by atomic size, but we'll get there. Then we need to rotate, and this is potentially the trickiest part, but there's a cheat for this. Rotate it so that the lowest priority group, and so that's going to be number 4, the 4th priority, lowest priority, is pointing backwards, i.e. is on a hash. It's very convenient if it already is back. You don't have to do anything. And then we look at the other 3 members, the 3 higher priority members, and we see if the sequence 1, 2, 3 is clockwise, which is R, or counterclockwise, S. Again, I think that counterclockwise kind of makes sense. Clockwise is the correct direction, the right direction. Counterclockwise is the wrong, sinister direction, the left direction. So what does this actually look like? Okay, here's our molecule. And we want to determine if it's left or right-handed, R or S configuration. I actually kind of misspoke there. I said the molecule left or right-handed, but we're really just talking about that carbon that is chiral. And first of all, we should make sure that it is actually chiral, because I might ask you to maybe on the exam, I would ask you to designate all the stereocenters in a molecule, and you want to make sure that what you're looking at is actually a stereocenter. Okay, so we've got the hydrogen, the chlorine, those are both different. There's an oxygen here, that's unique, so that's a different group, and then this ethyl group on the left. Okay, those are 4 different groups, so that is a chiral molecule, and that carbon is a chiral center, stereocenter. Okay, so we need to find the priority of those groups. So that's done with the highest priority being the largest in atomic size or atomic number. Atomic number is a more correct way to say that. So here's where you might need your periodic, hopefully not, but you might need your periodic table. What's the largest element that's directly connected to the stereocenter? Yeah, the chlorine. Second largest? Oxygen. Third largest? Carbon over here. And then if you've got a hydrogen, well, it's guaranteed to be number 4 because hydrogen is the lightest element. Okay, so done with number 1. We've prioritized all 4 groups on the stereocenter. Now we need to rotate the molecule so that the lowest, not mirror, but rotate the molecule so that the lowest priority group 4, the hydrogen, again, so this step here is if there's a hydrogen, That's what we're gonna be dealing with. Lowest priority group is back. Okay, so I made it hard on us, and we don't have this case currently, so we're gonna have to mess with the molecule. So in order to get the hydrogen to be back, right, it's leaning forward right now. So we just, sorry. So we need the hydrogen that's pointing forward to be turned around going backwards. So we need to rotate along this axis. Of course, it doesn't matter which direction we go, but we need to do a 180. Okay. This is where potentially your molecular model could come in handy, but I'll go ahead and actually what I'll do, no, I'm going to draw it out. I'm going to be good and draw it out properly. Okay, this is a rotation and not a mirror image. It's one of the reasons why when I did a mirror image up there, I drew in the mirror. And here I'm drawing an axis of rotation and then kind of reminding myself what direction we're rotating. Okay, so now that's step 2 done. We've rotated so that the hydrogen is backwards. Okay, and we need to put in our numbers here again. And now we just need to look and see if 1, 2, 3 goes clockwise or counterclockwise. So what is our configuration for that stereo center? Is it R or S? S. Okay, so 1, 2, 3. 4 we don't care about. And in increasing order, they go like that. That's counterclockwise. And so we have S configuration. Questions on how I got to that S answer? Okay, I told you there was a cheat with step 2, right? Rotate so that the lowest priority group is back. Okay, so what we did, well, here in our correct version where the hydrogen is pointing back, 1, 2, 3 goes counterclockwise. What about the wrong version where the hydrogen is coming toward us? It's clockwise, isn't it? 1, 2, 3. That's always going to be the case. Rotating the molecule from where the lowest priority group is toward you to behind you, need to stop doing that, is always going to flip the direction from clockwise to counterclockwise or counterclockwise to clockwise. And so if you're careful and you don't mess up which direction goes with which in which scenario, you can say, all right, here I've got the hydrogen coming towards me. And so if the hydrogen's coming towards you, that's not really how you're supposed to do it. But clockwise configuration of 1, 2, 3, in this case, doesn't mean R, it means S. Okay. So if the hydrogen is coming towards you, actually I'll call it number 4, priority number 4. Often it's a hydrogen. If number 4 is on a wedge, then the clockwise versus counterclockwise are backwards. Very convenient, but also potentially easy to mess up. Okay, in this example, all four elements that were connected to the carbon were different, and so that made assigning the priority pretty easy. But as we know, organic molecules tend to have a lot of carbon atoms, and so what's going to happen is we're going to end up with multiple carbon-based substituents on our carbon of interest, and so we're going to have to have a tiebreaker of some kind in between those. So example of that would be molecule like this. So first we need to assign priority. This is going to be the special part of this example. I think we can see pretty quickly that oxygen is the heaviest. So that's going to be our number one. And we have a hydrogen. So that's always going to be number four. So that's taken care of. The question is, are our left and right carbons 2 or 3? Which is going to make a major difference in the assignment of R versus S. If we get this wrong, we're going to get the configuration wrong. So this is important. The way we're going to do this is, well, first look at the actual atoms that they are. Okay, carbons. So we got a tie there. Now we're going to look at all of the other atoms, excluding the one that goes toward the stereocenter, that are attached to this carbon. Okay, so attached to the blue carbons, we have on the left, we have one carbon and two hydrogens, right? Those two hydrogens, so CHH. And on the right one, we actually have the same thing. We have a carbon, the next carbon in the chain, this one. And it also has two hydrogens. Okay, that is still a tie. All right, same atoms, same type of carbon atom, both with two hydrogens, and so that this does not help us to resolve the answer. Okay, so now we've got to go an additional step. Okay, I think you may be able to see at this point that we do have a difference in between those two carbons. Okay, so these atoms are still both carbon. The one on the left, though, and at this point, we're now going to exclude this bond because that's to the carbon that was already part of our tie-breaking scheme here. So we're going to ignore that and only look at the other three atoms. Okay, so that carbon is attached to two carbons, right? Those two methyl groups, and then it's got just one hydrogen on it. This tie was between those two. Okay, the one on the far right. Okay, this one, other than the carbon that was already part of the tie-breaking exercise, is attached to one carbon, and this guy has two hydrogens, CHH. Okay, so now we're going to compare our next round of tie-breaking, and who wins, left or right? Left. Okay, so left wins, and it is going to have a higher priority, so it's going to be number 2. Okay. And I think just by looking at it, you're like, okay, if we start going this way, where does it get busier faster? On the left. Of course, you should probably do this exercise just to make absolutely sure. But often if you've got a really sort of dense, busy structure, that's going to have a higher priority. That's extremely hand wavy. All right, so now all we have to do is say 1, 2, 3, go counterclockwise, so it's S, right? No? What did I do wrong? Hydrogen's coming toward us. So do we want to flip the whole molecule around or do we want to cheat? Let's cheat. All right. So hydrogen's coming toward us. So that means our clockwise versus counterclockwise, our S thing is going to be backwards from the way it should be, or the way it seems natural, at least to me, it seems natural. Okay, so 1, 2, 3 in this position are counterclockwise. So is that R or S in this case? R. Okay. Because in order for the clockwise counterclockwise to be in the kind of the sensical way where clockwise is right, the hydrogen has to be back. Okay. If we're doing it the cheating the wrong way, then we're going to say 1, 2, 3. Hydrogen is forward towards us on a wedge. So counterclockwise rotation of the 1, 2, 3. That gives us R configuration. If we rotate the molecule, we'll end up with H going back. Then we'll have a clockwise order of substituents 1, 2, 3, and that will also give us R. Okay, if the cheating method is a little confusing, or you were really insistent on saying you instinctively said S, make sure you can practice rotating the molecule, flipping it like a pancake, getting the hydrogen to go backwards, and making sure you assign the correct substituents to the correct numbers when it's rotated. Other questions on R versus S? Do we want to do one more example? We have time, so let's do one more. Let's do this bromine one that we saw earlier. I'm going to assign it a specific stereochemistry. So work on this for a second and tell me whether this is R or S. Let me figure it out because I don't know. One day I'm going to forget to turn on do not disturb and going to get an embarrassing meth leak or something like that. Make sure that doesn't happen. What do we think? R or S? heard an R. Do we like R? I think I like R. Let's make sure. I didn't write it out yet, so. Okay, priority. Number one priority is what? Bromine. Number two, left or right carbon? Right. So it's the right carbon because, well, we have two carbons, left and right, and they're both carbons. The carbons are carbons. The floor is made out of fluor. And so we got to go another step further and say, oop, okay, this one is attached. It's doubly bound to a carbon. And so for purposes of tie breaking, that kind of counts as being attached to two carbons. Whereas on the left, that one is attached to one carbon and two hydrogens. Then we've got our hydrogen. Oh, thank God, the hydrogen's going back, finally. All right, that's going to be number 4. But that's cool. As long as it's going back, we don't really care that it's number 4. All right, now the hydrogen's going back, so we don't have to do that step. And so we've got 1, 2, 3 going clockwise. Hydrogen's back like it should be, clockwise, and so that gives us R, stereochemistry, at that chiral center. So all of the compounds that I've showed you so far have only had one chiral center. And that's easy enough. Your mileage may vary. But there will occur cases where we have multiple stereocenters in a compound. And so what happens when we start, one of them's R, one of them's S, like how do we deal with that business? And so the relationship we use to describe some of those compounds, I should probably not talk and write at the same time. The relationship between those may be diastereomers. Okay. And to explain what a diastereomer is, we really need to make a comparison chart. And so this will also help us, I think, with enantiomers. Okay, so enantiomers versus diastereomers. So they are both non-superimposable on each other. If they were superimposable, then they're identical, right? Two compounds. If you can make a photocopy of one compound and put it right on top of the other and not be able to tell the difference, they're identical. Okay, so enantiomers and diastereomers are not superimposable, i.e. are not identical. Okay, big news. Enantiomers are mirror images of each other. Okay, this is just the definition that I gave you for enantiomers. They are non-superimposable mirror images. Diastereomers are not mirror images of each other. Okay, I know this is really conceptual, but the last point is going to drive home the difference between the two. Again, I said about enantiomers, the word enantiomer is like the word twin. So enantiomers must occur in pairs. Diastereomers two or more compounds can be diastereomers of each other. So we could have a set of 4 different molecules, and the relationship between any and all of those 4 molecules is diastereomers. Okay, it doesn't just have to be in pairs. And here's the key. Enantiomers differ from each other by the configuration of every single one of the stereocenters. In the examples we've seen previously, there's only one stereocenter in the molecule. And so all of the stereocenters in that molecule is just one. And so we just flip that one stereocenter and we get the enantiomer of that compound. But if we have a molecule with 10 stereocenters and we assign them all R and S, and then we flip them to reverse that assignment from R to S or S to R, for all 10 of the stereocenters, we get the enantiomer of that compound. But if we take the first 3 stereocenters out of those 10 and just flip those, leave the other 7 alone, then we get diastereomers. So these differ by the configuration of some but not all of the stereocenters. So if we've got 2 compounds and we change none of the stereocenters, well, they're identical. If we change all of the stereocenters, they're enantiomers. And if we've got a mess going on where some of them have been changed, but some of them stay the same, those are diastereomers. Okay, so let's look at an example of a compound with 2 stereocenters, and we'll come up with all the different versions of it and figure out if they're all, what the relationship is between all of them. Okay. First thing you'll notice, I have not drawn wedges or dashes. We're gonna make those up. So I'm going to tell you up front that this has 4 stereoisomers. It's actually 2 to the n. So 2 to the number of stereocenters gives you the number of stereoisomers. And what we want to do here is look individually at the relationship between each isomer. Okay, so we should be able to come up with 4 different stereoisomers, just not by, you don't even have to think in 3D. We just have to think about wedges and hashes. That sounds counterintuitive, and kind of is. Okay, so start drawing some hexagons here. So let's just start randomly assigning stereochemistry. This is like the only time you ever get to make stuff up. But here we go. Okay, so maybe they're both on a wedge. Or maybe they're both on a hash. We're not going to talk about chairs. I just coincidentally I drew a hexagon, but we're not going to talk about the chair structures of this. That's a whole nother can of worms. So these two, they're both on a wedge or both on a hash. We can also have 2 where they're different. So we can have the OH on a wedge and the methyl group on a hash, or we can do it the other way around. OH on a hash, methyl group on a wedge. Okay. So what is the relationship between A and B? Look at the stereocenters. Have we flipped all of the stereocenters or some of the stereocenters? All. So what relationship is that? Enantiomers. Okay. What about C and D? How many stereocenters have we flipped in that case? Some or all? Really? So we've gone here from a wedge to a hash, and here we've gone from a hash to a wedge. Might look like we've flipped the molecule upside down. If you think that I have, build a model and try it. You can't do it. So we've switched both stereocenters here. So these are also enantiomers. What about the relationship between A and C, which is the same, actually, as the relationship between A and D? Sorry, the arrows are going to get a lot here, but okay, going from A to C, the OH stays the same, right? It's on a wedge in both cases, but the methyl group has gone from a wedge to a hash. So we flipped one of the two stereocenters. That's some, but not all. So A and C are diastereomers. Told you A and D was the same relationship, so let's make sure that that's true. Okay, between A and D, the methyl group is on a wedge in both cases, but the OH has gone from a wedge on A to a hash on D. So we've changed one out of two, some but not all, of the stereocenters. So those are diastereomers. Okay. So now we can look at B and its relationship to C and D. Okay. So going from B to C, hopefully this is getting boring. Going from B to C, the methyl group is on a hash in both cases, but the OH switches. So we've switched one out of two stereocenters, some but not all. So B and C are diastereomers. B and D, the OH stays the same. It's on a hash in both cases, but the methyl group goes from a hash to a wedge. One out of two have changed, some but not all. That gives us diastereomers. Okay. How do we feel about enantiomers versus diastereomers? For some reason, I was never taught this, the differing by the configuration. And that's like if you remember one thing about enantiomers and diastereomers, that's what you should remember. Because if you can remember that, you figure out the relationships if you stare at it long enough. So that's kind of the key. This other stuff is nice. Like it's very good to know that enantiomers must be in pairs. And you can't have three compounds that are all enantiomers of each other. That's useful. But just make sure you can pin down that configuration relationship. Okay. I was very intentional here that I chose a compound with an OH and a methyl group, two different groups. Okay. So now I'm going to kind of ruin your day. And eliminate your trust in wedges and hashes using meso compounds. Okay, so meso compounds are kind of a wolf in sheep's clothing. So let's take the example instead where we have two OH groups. Okay. I'm intentionally starting with ones where they're opposite in this case. Okay, so now instead of drawing all the molecules and assigning the relationships, we're going to start with the molecule and say, okay, draw the enantiomer of that. Okay, so follow your rules. And the rule for enantiomers is we flip all of the stereocenters. I couldn't say just draw the diastereomer because there's potentially multiple of those, but draw the enantiomer. Yep, enantiomers are always pairs, so we can do that. All we got to do is flip all the wedges and hashes. But Dr. Eubanks, you say, are those different compounds? Couldn't we just take this, flip it upside down, and get that same molecule? Let's try it. So I'm going to use this axis here, and we're going to rotate it. Okay, so wish I could do a headstand here. That'd be helpful. But okay, so let's look at the bottom OH. Okay, in the beginning, that is going backwards. Okay. It's going backwards here. If we flip it up like that, it's coming forwards at us now, isn't it? Here we go. Piece of paper. Sorry, this is a really weird example, but okay, I'm going to fold it, crease it like so. Okay, so now we have this flap of paper going back. Let's say that's our OH group. Okay, we're going to rotate on this axis. Coming toward us now. So we can't get to that enantiomer structure by rotating it. We just get an identical molecule. So these two are enantiomers of each other. So that's the example where we have a wedge and a hash. The meso compound is kind of a combination of these two. Nope, that's not what I wanted to do at all. I wanted them both on a wedge. Sorry. Okay, so now we're gonna be like a robot. And we'll do the enantiomer of it. Okay, so to do an enantiomer, we flip all of the stereocenters. So let's flip all the stereocenters. So we go wedge to hash, wedge to hash. Okay, so this is a pair of enantiomers, right? Right? If we follow our example from above, that should be true. And then we should be able to do the same thing here. Rotate this, flip it upside down, and get a compound that's different from the enantiomer. Otherwise, they would be identical compounds. Okay, so we'll just check this to make sure. What could possibly go wrong? All right, so here we go. Here's my wrapping molecule. Okay, so both of the OHs, these flaps of paper, are coming toward me. We're going to do a rotation along that blue axis. So now we've reached the same compound that we said was an enantiomer. Okay? These are not enantiomers of each other. They're identical, even though we followed the process that should give you an enantiomer. Okay? So these are two different angles to view the same compound, and we call this a meso compound because it's going to trick you like this. You'll try to find the enantiomer, and you'll find that when you do that process of flipping all the stereocenters, you get an identical compound. So the short version of how to spot these without doing this meso compounds have a plane of symmetry, okay? Especially next semester, we're going to come back mega to planes of symmetry. We're doing NMR spectroscopy. I know that sounds really random, but we will. But you should start seeing these planes of symmetry here. So a meso compound has planes as a plane of symmetry. A lot of compounds do. But meso compounds have a plane of symmetry and have actually have chiral centers. So you couldn't argue that this is not a chiral center. It's got four different things attached to it. The OH, the hydrogen going back, the ring going left, which is carbon, 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 and the ring going right, which is the carbon with the alcohol on it. So they are certainly chiral centers. That's chiral. This is chiral. But the compounds themselves, the whole molecule, is not chiral. So they're achiral. Okay, so I'm not going to ask you to assign stereochemistry of meso compounds and try to get you to draw the enantiomers like this or something. But what I could do is give you two compounds and ask you the relationship between them. And say maybe I gave you those examples at the top here. And I said, what is the relationship between these two compounds? You might say, okay, both of the stereocenters are flipped, so they're enantiomers. That would be the instinct. But you got to look at it and say, ooh, hang on. We've got a plane of symmetry going through the middle here. And I don't know about you, but when I see that plane of symmetry, I'm like, okay, I'm not really convinced that these are identical. In that case, you either need to build a physical model or at least model it in your head and say, okay, are these really enantiomers? or can I rotate it in some way to make the same compound? I have questions on meso compounds. Okay. Make sure you take a good stab at the extra homework problems. The exam is the exam is a lot like the homework questions. So if you can review those and get those right without looking at the answers, you should be pretty well prepared for the exam. It's going to be on Thursday, so next time you'll have the whole class period, 75 minutes. It'll be worth 100 points, so 10 times a homework assignment. Free response, currently it's 3 pages front and back, 11 questions. That could change. You'll have the IR chart, so you don't have to memorize any of that stuff. You'll have a periodic table. You should have your molecular modeling kit. Either you can put it in plastic bags, or if yours comes in a clear case that doesn't have any like the booklet in it. So if you have a clear case that you can take the booklet out of, that's fine. But if your case has materials printed on it, it's a no-go. No stencils. Okay, so practice freehand drawing these things because you'll have to do that more and more and more as we go on. Questions about content or exam? Yes.
Okay, so a clear case, I guess, without.
Oh, perfect. Thank you. I was hoping somebody would have it. No, I'm good. I'm holding it. So here's the little booklet of cheat sheet stuff. However, his kit is just totally clear with no materials in it or anything. This is fine. And I think a lot of manufacturers have started to do like that for that reason. But
Would all three response or you're like?
there are a couple of multiple choice questions. Yes. Sorry.
Because I have the function of the chart, you need to memorize all.
You need to know that. Yep.
Is it equal from each chapter, or is it like heavy with each chapter?
It's pretty equal. Actually, I'd say it's very equal. Maybe a tiny bit more on this last chapter just because there's more material. But not by a lot. So it's pretty even. Yes.
Are you providing the sheets that we're allowed to use, or do you need to print them and bring?
Oh no, they're included in the packet. Yeah, everything's included for you. All right, I will see you on Thursday. Just make sure you're here on time. Thank you.